Welcome everybody to this installment of the modeling series. I'd like to invite Ed Lee from Berkeley, who's made a career of making software to model anything pretty much in the world. So yeah, welcome Ed.
Thanks. So I'm Edward Lee from Berkeley, and I thank everybody for your interest in this project. And I am a little unfamiliar with this particular interface, so I don't know. I guess you'll need to probably interrupt me by audio with questions at any point. And as far as the local recording, I'm going to record this, but I'm going to edit out anything that isn't just my own content. I find it useful to then have recordings like this for, reuse, but my recording will only have my own content. So feel free to ask questions that you don't want recorded. No problem with that. Okay. All right. So the topic today is to talk about modeling, and this is motivated by a very long-term project that we've had going at Berkeley called the Ptolemy Project, and that has resulted in a pretty substantial piece of software called Ptolemy II. And so there's a lot there, actually, and one of the issues is how do I distill that into a reasonably short period? And I struggled with this a little bit, and so I might not get it right, but I'll attempt to try to give you an overview of what this project has been about and what the open source software that we've created is able to do. It's a very multifaceted project. It has about 26 years of work, which is actually, in a way, it's a real stretch to call it one project. It's not. It's several dozen projects and 37 PhD theses with hundreds of papers and various spin-off projects. There's the Kepler system for scientific workflows that some people might be familiar with. There's a spin-off called Cape Code. There's another spin-off called Sci-Fi Sim, one that I'm very active with these days, which is Lingua Franca, which I'll tell you a little bit about moving through. So I was mentioning that this is a pretty long-standing project, a multifaceted project with a lot of background. A key resource for this, if you want to dig in deeper to any of the things that I'm talking about, is a book that me and several of my former students and colleagues around the world put together that is a free download. So it's actually a self-published book, and you can get it from this URL that's on the website, ptolemy.org/systems. And it's a pretty comprehensive view. It doesn't have some of the most recent stuff because we finished it 3 or 4 years ago and haven't added chapters to it yet, but it has a lot of the more mature technology behind it, and so it could be a very useful resource. So the software itself, Ptolemy II, has a few principles that I'd like to highlight. One is that it actually does not realize a single way of doing modeling. It's actually in many ways a laboratory for experimenting with ways of doing modeling. And we've built quite a number of rather different modeling tools within this framework. And the way that a Ptolemy model is constructed is that it includes one or more directors, where the director is this little green box. So this DE director is a discrete event director. And the director defines what the interaction semantics are between the components of the system. So each of these little graphical boxes is a component, and for the discrete event director, the interaction between components is through time-stamped events. And I'll try to give you a sense of what some of the different directors are that we built, but I'm not going to do a survey of the different models of computation. I'll just give a few examples. There is a fairly large library of reusable components. But I personally find the system more useful as a framework for developing custom components. So you can think of it as a programming framework more than as a framework for assembling pre-designed components. But there is a pretty rich library of predefined components that you can put together. And some of the spin-off projects like Kepler, Kepler has really focused on enriching that library with components that have a lot of sophistication in doing kind of big data, machine learning integrations with R and statistical packages and things like that. And so, you know, those reusable components can be pretty useful to people at times. So, to give you a sense of just how hard it is to give a brief presentation of it, the software, according to this Black Duck website that does automated analysis of open source software, I just checked this 2 days ago. And 2 days ago, it said that we had approximately 75,000 commits, 208 contributors, 4 million lines of code, mostly written in Java. And it tells us it's well-commented source code, has a well-established mature code base, and it took an estimated 1,180 years of effort, which blows my mind. I can't account for all those years. I had no idea that we were that old, but in any case, that's what their model estimates for the code base. The other thing that I'd like to point out is it's open source software with a BSD style license, and the code is written to be read. One of the principles that I've always imposed on the project is that I treat the code that gets checked into our repo as a form of publication. And so this is a little snippet of code, and you can get a sense that the number of lines of Java code are significantly outnumbered by the comments. The comments are complete English language sentences. There's a common code style that we've enforced and forced upon all 208 committers. So the goal there is to reduce the fatigue in reading the code, because once you get used to the code style that's used here, you'll find it used very uniformly throughout the entire code base. So the code is really meant to be read, not just executed. Now, one of the key properties of Ptolemy, and I think one of the key innovations, is this notion of having some flexibility with regard to the model of computation. Pretty much any modeling and simulation tool that you obtain out there, with the exception of Ptolemy II, has a single built-in model of computation, and you have to basically buy into that one model of computation. But Ptolemy II is not like that. It has continuous time models, for example, which will use, basically, you construct models by describing ordinary differential equations, and it has a differential equation solver. We have discrete event models, which are kind of similar to a lot of the discrete event simulation tools. We have synchronous reactive models, if you like synchronous languages, and we have a variety of concurrent asynchronous communication models, such as process networks, rendezvous models, and data flow. And there's also a few sequential models like state machines and modal models, which I'll show you a little bit about. And one of the most interesting things about Ptolemy II is that you can actually combine these models of computation into a single model. And I'll try to give you a little bit of a sense of how that works. The other thing is that the software architecture is designed for experimentation. So it has, even though it's over 1 million lines of code, it's divided up into very well delineated packages, and the packages, some of them are really completely independent of the rest of the system. So for example, there's a very well developed graph package that has a lot of graph theoretic manipulations in it that really doesn't depend on any of the other packages. The data package is where all of the support for a rather sophisticated type system. It's a Hindley-Milner type system in Ptolemy II that does type inference, so that model builders don't have to put a lot of effort into the type system.
Actually, can you clarify, what is that type system? I've never heard of that name.
It's so the Hindley-Milner type system is similar to the type system that's in ML and SML. And so it's a type system that, first of all, it's very polymorphic. So a lot of the components are very flexible about what data type their input ports accept and their output ports produce. And when you connect them with other components, the data types will be inferred. So any component that constrains the data type imposes those constraints on the rest of the model. And so the inferred data types propagate throughout the model from those constraints. So built around this central infrastructure, there's then what we call the domains, which implement the particular models of computation. So for example, the discrete event domain, which I showed a little snippet of, is realized by a discrete event director and a few other Java classes, plus a library of components. So there's various spin-offs, as I mentioned. This is a little snapshot of Kepler, which has been one of the more successful spin-offs. It's quite popular in various scientific modeling communities. And interestingly enough, I was not a leader on the Kepler project. In fact, Bertram Ludescher at UC San Diego was really the one who started it, and then various other people like Ilge Altintas really ran with it and created a really beautiful spin-off. And it's completely compatible with Ptolemy II. It's an extension, a strict extension. So they in fact use our repo and use our production code as a core part of Kepler. So it's a strict extension. Anything you build in Ptolemy II can be used within Kepler. And their emphasis has been on a lot of big data, supercomputing applications. This was done at the Supercomputer Center in San Diego, and so forth. So this is one application that, demonstration application that uses web services to extract from databases genetic information and then represent it in various ways. So I'd like to give you a little, yeah.
This is Malcolm. I'm confused at the goal of Ptolemy. When you first did it, it was multi-rate signal processing seemed to be the core. And right. This example seems like mostly just a graphical programming interface to some streaming data. So yeah, what's in between all that?
Yeah, in fact, that's a good question and a good segue. Kepler advertises itself as a workflow management system, and so it really is mostly about the creation and documentation of workflows, each of which the components are rather large. The project, as you pointed out, did start out in the signal processing space, okay? And rather than do pure PowerPoint, let me go and actually do some real Ptolemy. So if you start up our graphical user interface, you get this first welcome window. And the most useful link, in my view, if you're just starting with this, is this Tour of Ptolemy II link, which takes you through a bunch of the capabilities that have been developed over the years. And if I scroll down to signal processing, which is the deep roots of the project, that's when it started 26 years ago, it was very much about signal processing. And this is a simple signal processing application. It's got components like this audio capture component, this FFT component. These come from the library of actors over here. And you can scroll down and find, for example, here is the audio capture component came from this audio sublibrary of the signal processing library. And each of these components is quite well documented. So if you request the documentation, you get this description of what the component does, what its parameters mean and what they are. This documentation is actually derived from the source code, as is more conventional JavaDoc documentation. So you can go and look at the JavaDoc documentation that's familiar to Java programmers. But you can also look inside. You can open this guy and actually look at the source code. Okay, so and you'll actually see that the documentation in the source code is where both the JavaDoc and the online documentation come from. So if I run this particular model, it will perform an FFT analysis of the audio signal that it is picking up. You can recognize this if I whistle, for example. The volume of my microphone seems kind of low. I hope that doesn't, you guys can hear me okay, right? Because normally I see much bigger spikes in the audio signal here. But don't know if there's a way to adjust the microphone volume, but I assume you would have complained by now if the volume was too low. But for some reason, the microphone volume is lower than it normally is. So if you run through this this tour, you'll find actually a pretty incredible range of very different kinds of things. So, for example, hybrid systems. Here is a hierarchical model that models friction between two masses, where one mass is sliding on top of one another. When I run it, I get a plot of the velocities of the signals over time. And what happens is that the two masses are starting out together. One of them is moving, and then one of them starts moving fast enough that they start sliding with respect to one another. And then there's impulsive forces. So there's an outside force that's hitting this that is causing an abrupt change in velocity, and it's having an effect on the second mass and so on. And this is actually constructed by combining models of computation. So the director here is the continuous director. So it's doing continuous time modeling. The impulsive forces are being generated as discrete events by this discrete clock. This modal model is actually a finite state machine with two interesting states besides an initial state and transitions between states. And these states are hierarchical. So one of these represents the mode where the two masses are stuck together. So they're moving together. The second one represents the mode where they're sliding with respect to one another. And if you look inside these, you can see, for example, that if the two masses are sliding with respect to one another, well, yeah, you can see actually that there's a differential equation that's being represented here in a Simulink style, where these are integrators. And unlike Simulink, there's this impulse input to the integrator, which is a very faithful representation of the mathematical Dirac delta function, which is exactly what it does. And I'll talk a little bit about the modeling principles behind this, which to me have been some of the most interesting results out of the research project. We've put a lot of effort into the model of time that's used and the ability to have very rigorous representations of fairly sophisticated mathematical operations, such as Dirac delta functions, which can cause abrupt transitions in velocity, which are not just approximations of smooth transitions. These are actually, if I zoom in, they are zero-time transitions, as you would get from a mathematically idealized Dirac delta function.
So should I be thinking of the continuous director as a differential equation solver?
Yes, a differential equation solver that supports hybrid systems and mixed signal models. So you can have discrete events combined with continuous dynamics, and you can have modal models where you switch between modes of operation.
So the difficulty, and I'm thinking from my prior days in Department of Energy, is numerical stability seems difficult to maintain when you do that kind of stuff. How do you?
Well, actually, in some ways, numerical stability can be easier with modal models because there's two phenomena that this framework enables, right? One is that you can keep a model operating within a regime with which it's comfortable. And if there's a regime in which your model, in which an alternative model would work better, then you represent that as a modal model and you switch into that alternative regime. So it enables you to actually use simpler and more robust differential equation models in a very clean way, and then switch between those models when one of the models becomes very stiff, for example. And the other thing that you can do is you can isolate components of your model that have very different rates of temporal dynamics. So you don't have to have a single ODE solver, which will, if you have a portion of your system that's very stiff, for example, then the sample rates of your solver will get very fine. The period of the samples will get very fine, and the entire model will bog down, even the parts that are not stiff. And in Ptolemy, you can separate out these parts and run them using different solvers and compose them hierarchically in this mode. So those two mechanisms actually enable you to build models that I think are a bit more robust than what you can do with some of the other solvers.
So when people talk about models like this, presumably these are dynamically all these different resolutions are interacting, right?
That's right. Yes,
So
they can be interacting via discrete events or via continuous signals.
right, and then it makes perfect sense. I mean, this is like a standard multi-scale decomposition. And then how difficult is load balancing when you try to use that approach?
So in this project, we have not done much with parallel execution of these models. The spin-off project, Lingua Franca, which is where most of my activity is these days, is very much about parallel and distributed execution. So I'll talk a little bit about that later. But in Ptolemy, you won't see support for parallel execution.
Yeah, makes sense.
Yeah. Okay, so let me go back to here. So yes, when we started the project 26 years ago, it had a very strong emphasis on signal processing, and to some degree that has actually held throughout the project. So for example, one of the more recent ones is to build a library of machine learning and inference capabilities. So this is an application that was developed by one of my recent PhD students, Ilge Akaya, which shows a robot that is moving in circles using a sensor that can only detect range to identify the source of a stimulus. So it takes into account its motion as well as its sensing data. And it's using particle filtering to do this. And so, in fact, her PhD thesis was very much about a machine learning toolkit built into Ptolemy II, which has things like hidden Markov model support, particle filtering, support state space models, and various standard statistical models. The Kepler project has also done a lot of work in integrating a lot of machine learning and statistical analysis into Ptolemy II as well. So this is a recording of one of Ilge's robot combined. It's a trajectory planning and target identification combined mechanism, again, using particle filtering. So this is the more recent manifestation of the signal processing work. Now, even though we started with signal processing, we progressed pretty quickly to heterogeneous modeling and simulation. And I showed one example of that, the friction example already. Here is a simpler example that is one of our standard demos, which shows two masses on springs and models them using a modal model again, where you use a different model for the scenario where they're stuck together compared to where they're separated. And, this is a sort of a very simple instance of a model that if you try to write down a single differential equation for the behavior of this thing, it's exceedingly difficult to do because of this transition between modes of operations. And so by being very explicit about the mode switches, you can come up with much simpler differential equation models. So in particular, shown here at the lower right is a simple second order differential equation for the mode where the two masses are stuck together, so they're behaving as one mass with two springs attached to them. And I'll come back to this question of these discrete mode transitions, because I think that this is one of the parts of the project that has been done in a very rigorous way. Another use of this heterogeneous modeling capability is to do virtual prototyping. So we did a lot of work with funding from SRC and various companies on being able to do virtual prototyping, and the test cases were all in the avionics space. So this was an example of a virtual prototype of a generator on an aircraft driven by the aircraft motor, and with a combination of low-level feedback control and supervisory control, and an assessment on how the controller would behave if it was executed on a single processor machine or on a on a dual core machine. And so that kind of virtual prototyping is facilitated by this ability to do this heterogeneous modeling. So again, these were mixed continuous and discrete subsystems, but combined also with alternative target architectures, and the target architectures themselves are also modeled too. There have been several projects based on Ptolemy II that focused on tool integration. So one of them is we built an FMI toolkit. So FMI is the functional mockup interface, and it's something that comes out of the Modelica community. And Modelica is a very well-established tool for doing quite sophisticated continuous time modeling. So you can integrate Modelica models with Ptolemy II through this FMU interface. And this is an example of such an integration. This insert is a graphical picture of a model constructed with a Modelica tool, which is then exported into what they call a functional mockup unit, which is then integrated into a Ptolemy model, and then you can execute these. And our focus, much more than the FMI effort, is on hybrid co-simulation. So in particular, mixing the continuous dynamics with discrete mode transitions and discrete event systems. And there's a fairly recent paper that really goes in a deep dive into the fundamentals behind this. This is a requirements paper. It was done jointly with people from IBM and Berkeley, and KTH, although Broman was at Berkeley when he was doing most of this work. But nevertheless, this paper really talks in some depth about what's behind the principles behind really rigorous hybrid co-simulation. So when we moved, I would say, one fair characterization here is that we started in signal processing, we moved into control systems, we moved into more amorphous kind of control systems that would integrate supervisory control and higher level decision making. And from there, we went whole hog into the broad problem of embedded systems and cyber physical systems. And so here we became very focused on mixtures of physical dynamics and computational elements and network fabrics and the interactions between all of these components. And this led us down quite a number of different paths. We built a fairly elaborate infrastructure for modeling wireless networks so that we could build good simulations of wireless network fabrics. You saw just a minute ago a little snippet of something that was very much focused on how a piece of embedded software would interact with a physical plant and how the properties of the computational platform could affect that interaction. And so this question of cyber physical systems became really very much the focus of the project and continues to be. So the real research questions are, how do you design, model, and analyze such systems? How do you achieve the quality of service guarantees? How do you provide safety guarantees in the face of failures? And how do you guarantee properties of the system? So to give you an example of where this led us, I'll show a little simple demo that we built under an SRC-funded project called the Terraform Project, which ended a couple of years ago. And this one was using Ptolemy II to build a virtual reality infrastructure. And the idea was that a camera would be used to recognize elements in the environment. So in this, at the upper right here, it recognizes a traffic light, and then it dynamically downloads a component that it runs as a Ptolemy component that provides a virtual reality interface to that traffic light. So this mock-up is saying, well, it's telling the driver that there's 5 seconds left on this green light using a heads-up display. In a more industrial setting, you could use this, for example, if you recognize devices in an industrial setting, you could bring up user interfaces on a screen that would allow you to both monitor the state of the devices and also interact with them. This is a video of a demo of this system that is conducted in my office using this spin-off from Ptolemy that we called Cape Code. And it's called an augmented reality office. And this is it just showed the Ptolemy model that's running. And now the video camera image, that's my office, which I haven't been to in several months now. The component just recognized a tag on the screen, which represents a service in the audience. And the service is an audio service. It's just a toy, right? You can select an audio clip that the audio service will play. You see the camera scrolls around and recognizes another service. This is now a lighting service. And the software now actually downloads from a server the code to provide a user interface to this lamp, which is then being used to turn on and off the lamp and control the color of the lamp, and so forth. Okay, so this, I chose to show this in part to emphasize that the project moved really quite far past modeling and simulation towards mechanisms that are more focused on actually building implementations and deployable systems. And the Lingua Franca spin-off, which I'm very focused on today, is very much about that. But just to give you a sense of the components in Ptolemy, so this is a Ptolemy actor that is designed for use with the discrete event director that produces streams of frames of video from a video camera, and then a recognizer, an image analysis component. In this particular prototype, it's just recognizing these QR tags that are put in the field of view. It identifies the tag, and then there's a custom JavaScript bit of logic here to figure out what to do with the tag. So this ability to put in your own components, you can actually design your components in JavaScript, in Java, in Python. Those three languages are fairly well integrated, so you can build your own application logic in a Ptolemy component in any of those languages. I rather like using the JavaScript framework because it's very interactive, and you don't have to recompile things to instantiate your components, and it's very convenient for really rapid prototyping where you create a new custom component relatively easily. This is a hierarchical model, so there's actually more components behind it, but it is the component that actually downloads from a web server the code that it's going to execute to build the user interface. And then there's another bit of custom JavaScript logic that actually builds the HTML code, which it feeds then to a reusable component that creates an interface in the browser. Okay, so that project led to this spin-off that we call Lingua Franca, which is saying, all right, if we're moving away from modeling and simulation towards deployable software, performance and footprint are going to become a big issue. And Ptolemy II, the focus has never really been on performance or footprint. So for example, it doesn't have much in the way of support for, doing parallel execution of your simulations on multi-core. And the footprint is quite substantial. It's a bunch of jar files that encapsulate 1 million lines of code. So the Lingua Franca spin-off focuses very much on taking what we learned from this mechanism for building and prototyping deployable software and seeing how far we could push performance. And so this is built on the discrete event model of computation in Ptolemy II, and it makes a few extensions to the discrete event model of computation because it was a clean slate redesign. And it really has surprised me in how fast and lightweight it is. So you can create discrete event models that translate into standalone C programs that occupy only a few tens of kilobytes. So they're very deployable. They're extremely fast. On my own laptop, I measure it with some of our test cases up to 23 million reaction invocations per second per core. And if there's enough concurrency in the application, it'll use all 8 cores on my laptop without compromising determinacy. So that means on my laptop, I can get up to about 200 million reaction invocations per second, which is several orders of magnitude faster than I've ever seen in any discrete event simulation tool. So this is actually deployable code, and it's a clean slate redesign based on the discrete event mechanism in Ptolemy II. So in this, since it was a clean slate redesign, we also have not yet built a graphical editor for it. We have instead a graphical visualizer, which was actually built by colleagues in Germany that we've been working with. And so the graphics gets constructed on the fly while you build your program textually. And we have a really rather nice IDE, Eclipse-based IDE, which is optional. You don't have to use it. You can use an ordinary text editor and an ordinary command line compiler for it. But the IDE really gives you a lot of help in building these programs. All right, so that was kind of a whirlwind.
Let me ask you something about the system and the design. I guess as the system grows, it seems like it starts to approximate the more complicated component-based networks like Java beans and those, like big things or microservices. Maybe so. I'm trying to figure out what the boundary is. So maybe can you describe what it's not good at to understand kind of the space you've carved out with this design?
I'm sorry, the audio was a little bit garbled. What it's not what?
Oh, what it's not good at, because in its full fruition, this is just a component service, which it's not. It seems like you really had a much more narrow focus. So can you maybe describe the focus that makes a difference?
Yeah, I think that's a fair question. So one of the things is that if you're interested in partial differential equation modeling, for example, finite element methods and things like that, we've never built a Ptolemy director for that, and so you'd be kind of on your own to build in that kind of capability. The other thing is that unlike the Lingua Franca project, we never really worried that much about performance. I mean, we did sort of we tried not to do stupid things, right? But the goal wasn't to create the fastest simulator. The goal was to really identify the principles behind a really clean semantics. Okay, and I think the objective there was really to put a stake in the ground about this is how you should do modeling in any tool that gets created. I'll emphasize that a little bit, assuming I have enough time, when I talk about this model of time question, because I think this is one of the key takeaways from this project, and it has had a very big influence on the Lingua Franca effort. And in the Lingua Franca effort, we've shown that you can be very rigorous about the style of modeling without compromising performance. So I've talked about a little bit, or at least hinted at, our obsession with determinism. Okay, that has been an obsession in the project since the beginning. The models are representing concurrent systems, but every one of the directors that we've built, some of them are actually capable of non-deterministic modeling, but they discourage it, right? And you don't get non-determinism by accident. You have to deliberately build it into your models. So your models will behave deterministically in a repeatable way by default, always. And I explained also the emphasis on heterogeneity in that, you can mix different models of computation. What I'd like to talk about now is a principle that's a little more subtle, and I think that it's one that it actually took me a long time to realize, which I like to describe as a difference between engineering models versus scientific models. And in some ways, I think that maybe this blurred boundary in Ptolemy II is actually representative of a confusion that I had in my career for many years in not understanding the distinction between these two kinds of models. Okay, so I'd like to just spend a couple of minutes on this principle. So this really has to do with the question of not confusing the map and the territory. Right, the map is the model, the territory is the actual physical space, and Solomon Gulam famously said, you will never strike oil by drilling through the map. So it's all too common for people to confuse the map and the territory, and that really comes to play when you go to choose a modeling paradigm. So for example, you might choose to use differential equations based on a confusion between map and territory, thinking of your differential equations as if they were actually the territory rather than a model. Okay, and I'll explain what I mean by that in just a second. It's also extremely important to understand the purpose of them. So let me dive into this with an example. Right, so suppose that we use Newton's laws to describe the motion dynamics of a simple system like this Newton's cradle. Okay, now Newton's cradle is going to take a little more than Newton's laws because it has the collisions between the balls. So it fits very nicely the examples that I've shown before. But nevertheless, you have a modeling universe where you can write down Newton's second law, as you can see at the top of the screen here. And then you have the physical thing in itself, which is the thing you're trying to model. Now, you could use your mathematical model of Newton's laws to come up with a simulation. And the simulation is going to look pretty different from the video that I just showed you of this actual thing in itself, right? This is an image created by Dominique Toussaint, an animated image. And I love this image because he sets it on top of a copy of Newton's Principia. And it's got beautiful computer graphics, rendition, with nice shadowing and so forth. But it's clearly a simulation model. It's too perfect, right? And this is a video of an actual Newton's cradle that I bought from Amazon for $6, including shipping. And it's a piece of crap, right? I mean, the balls in the middle are supposed to stay still, and they don't. It's just it's a very poor realization of Newton's cradle. Now, the question is, which is at fault? The model or the realization? And that really depends on what your purpose is for the model. So the distinction that I realized after so many years is that in science, the value of a model lies in how well its behavior matches that of a physical system. But in engineering, the value of a physical system lies in how well its behavior matches that of a model. The goal of an engineer is to create a physical system that behaves like a model. And that's a different use of modeling. So these two uses of models are almost mirror images of one another. And of course, any scientist or engineer will actually end up using models both ways. And throughout my career, I have used models both ways, but I have frankly often confused which way I was using it. I thought I was using it one way and I was actually using it the other way. And the way you build your models really is profoundly affected by which of these you're trying to accomplish. So another way to see this is that, a scientist asks, can I make a model for this thing? And an engineer asks, can I make a thing for this model? And if you look at this Newton's cradle example, to a scientist, the model is flawed. It failed to identify the particular features of the physics that caused the balls in the middle to move when they shouldn't have moved. But to an engineer, the realization is flawed. And of course, the reality is that both are flawed, right? But the value of your model depends on which of the two you're emphasizing. So engineering is about making the thing match the model rather than the other way around. And if you consider chip design, right, if I have a circuit diagram A circuit diagram is a model ultimately for how I want the electrons to slosh around in silicon. And if I give you a piece of silicon that doesn't behave like the model, that piece of silicon is junk. It doesn't mean there's anything wrong with the circuit diagram. It is not incumbent on the circuit diagram to match the silicon. It's incumbent on the silicon to match the circuit diagram. And so that use of models is really very different. So here I can distill this principle in one very bold slide, which you will probably laugh at, and I won't blame you for laughing at it, okay? But I like it, so I'm going to present it anyway. So we have the things in themselves, as Immanuel Kant would call them, at the bottom of the screen here. So these are the actual physical artifacts, okay, the physical world artifacts. And then we have models of those artifacts. And if we're doing is focused on the science side, we're trying to build models to match the things. If we're focused on the engineering side, we're trying to build things that match the models. Now, of course, we don't typically work with just one model. We're often working with more models. And in fact, these more models will be related to our previous models through, for example, abstraction and refinement. So I might take a model that's a more abstract version of a system or a more refined version of the system. And the relationship between models is always a mathematical relationship, and really neither science nor engineering, but rather mathematics. So here you have it, science, engineering, and mathematics all in one slide. And that's, of course, audacious and ludicrous, but nevertheless, it's, I think, useful for understanding certain things. So for example, if I have specifications or requirements, those fall into my more models category. I then have a detailed design. That's in my models category. I then have the thing in itself that hopefully matches, behaves like the model, in which case I'm doing engineering. And if the specification is actually an abstraction of my model, or the model is actually a refinement of the specification, then my thing in itself has met the specification. So this framework gives me a way to actually make statements about the thing in itself using my model. So another way to think about
let me ask you, since we're here, have you thought about providing a support for like tuning parameters, reverse computation, or some kind of support for Bayesian inference on top of Ptolemy?
There is some support for Bayesian inference that was built into Pilot, which is this machine learning toolkit. We have talked about parameter tuning, and you can build Ptolemy models that will tune parameters based on experiments. But to be honest, we've never really developed a framework for that. You can build it. It's actually a fairly common thing that people do with Kepler because, you know, it's a fairly common workflow to do that kind of thing. And they describe it as a workflow to do the parameter tuning.
That makes sense. But now, so if you have a black box parameter tuner, that actually makes perfect sense. You can just strap it around. If you want to do something like gradient descent, you have to maintain enough of a history to do backwards differentiation. Is that easy or difficult in the framework?
It's hard to answer that. I guess I showed earlier a little snippet of a video from a robot path planning application, right, that was doing target identification and path planning. And that is doing actually model inference using gradient descent. So now I can't say that it was necessarily easy for the student who created that to create it. She wrote the actors that do that, and those became then reusable actors in this Pilot toolkit. But you know, it's to be honest, I don't know how complete it is, or you know, I mean, there's not been a lot of other people who have used her toolkit, so I don't really have a definitive answer for that question.
No, makes sense.
Yeah. Okay. So So George Box famously said way back in '87, essentially all models are wrong, but some are useful. It took me a long time to realize that this statement is about scientific models, because he's assuming that it's incumbent on the model to match the physical system rather than the other way around. So if you think about the corresponding statement about engineering models, you would say, essentially all system implementations are wrong, but some are useful. Okay. So the reason that I bring up this principle is that Ptolemy has done both kinds of modeling in very different kinds of projects. But I think it's fair to say that I didn't realize this until very late, that the emphasis of the project has been on the second, the engineering models. And so, for example, our focus on deterministic models and getting repeatable behavior. Well, the physical world often doesn't give you repeatable behavior. So when you're trying to construct scientific models, you may in fact want to build in the stochastic behavior of the system. And that has not been quite as much of an emphasis in the Ptolemy project. There is pretty good support for it, but it really hasn't been the emphasis. I would say the emphasis has been much more on this engineering style of modeling. So when you choose the modeling strategy, you need to know what question you're asking. So is the question whether your models describe a thing in itself faithfully, or is the question whether you can build a thing in itself where the behavior will match that of your models with high probability? So in the context of cyber-physical systems, I think our emphasis has been on the second of those two questions. And of course, we do want to be able to model pre-designed physical components here, rather than do everything as a specification. So if you have a DC motor, for example, that needs to be part of your system, I'd like to use a scientific model of a DC motor and then use that to then build engineering models for the software that's going to run on the computational platforms. Okay. This particular example that I showed earlier, well, is this a scientific model or an engineering model? Well, if you look at it, it's not a very good scientific model, right? It seems to defy gravity, for example. These springs aren't bending downwards. In fact, there is no gravity in this model, so it probably wouldn't be a very good scientific model of the graphical system that's being described here. On the other hand, the actual inspiration behind this model was in accelerometers, silicon accelerometers. The way that silicon accelerometers work is it's a microelectromechanical system where you float silicon fingers that are suspended above the chip and that bend when the chip accelerates. And then you measure capacitance because the bending moves the position of the silicon fingers and changes the distance between two capacitive plates. But one of the interesting problems that they had when they first developed these accelerometers, which was done at Berkeley, by the way, in a lab one floor down from my office, was that the silicon fingers kept colliding with the other fixed capacitive plate. And so they designed a feedback system that would inject a force that would countervail the motion of the finger. And then they discovered, Mark Lemkin in his PhD thesis, discovered that he could use the feedback control signal itself as a measurement of the acceleration. It was a beautiful design. And in fact, he did a design where the accelerometer immediately gives you a digital representation of the acceleration, not an analog representation that has to be then converted into digital, because his feedback control system was essentially a bang-bang controller that was already digital. And so the output of the chip was an immediate digital reading of the acceleration. And so that invention was what made silicon accelerometers take off. And the first big application was airbags in cars. And, for that, this model that's shown here could be viewed as an engineering model for a feedback control system that would apply this countervailing force that would that would keep these balls from colliding. Okay, so it's kind of a nuanced mixture between scientific modeling and engineering modeling here. But I would say the emphasis has been very much more on the engineering model. Now, one of the ways that you can tell that the emphasis is on engineering model, if you look at the plot of the velocities of these masses versus time, you'll see that there's instantaneous jumps. Of course, you don't get instantaneous jumps typically in a physical system. There's going to be some plasticity in these balls when they collide. They're going to bend, they're going to impose on each other. You don't get truly instantaneous jumps, but the modeling framework uses instantaneous jumps. And it's a choice you would only make when you're in a modeling regime where that's a pretty good approximation, and you're treating it more as a specification of the kind of behavior that you want, and then you want to build your physical system to come close to that specification. So this is where I'm going to talk very briefly then before I close about models of time. So what is time? I mean, a lot of Ptolemy is about the trajectory of a system in time, and physicists don't have a good handle on what time is. Okay, there's been lots of different views of it over history. Carlo Rovelli, in his recent 2018 book, says the nature of time is perhaps the greatest remaining mystery. Now, typically when people do modeling, they just say, oh, we'll just use Newton, right? Newton's model of time, and we just run with that. But Newton's model of time, it turns out, has trouble with the concept of simultaneity. Okay, so an event A is simultaneous with an event B if no observer can see that one event occurred and another did not. Right? But this requires a well-defined notion of an observer. So one of the things we've done over the history of this project is really dive deeply into what do we require from a model of time. And here's a few of the requirements, but let me just zero in on a particular example, this one, okay? And I ask you the question, what is the momentum of the middle ball as a function of time in the model, okay? And you might say, well, it doesn't move, so its momentum must be zero. But its momentum can't be zero at all times because the momentum of the left ball transfers to the momentum of the right ball through the middle ball. So how would you model this mathematically? Well, a straightforward way to model it is with a momentum, or I guess what's written here, I guess, is a velocity that is instantaneously non-zero, okay? But that doesn't last any time at all. It remains non-zero for zero time, okay? So, but it's not a Dirac impulse. If you integrate this curve, you get zero, which is why the ball in the middle doesn't move. But any discrete representation of this will actually be ambiguous. Any discrete representation, no matter how you do it, you can prove mathematically that every discrete representation of this is ambiguous. You can't just use samples to represent this. So the problem here is that there is really no semantic distinction between a discrete event and a rapidly varying continuous signal. And in Ptolemy II, we do make that semantic distinction. And the way that we do it is we use a model of time that we call superdense time. So physicists are used to modeling signals as functions of the reals. We say, no, sorry, that doesn't work. We model them instead as functions of a superdense timeline, which is the reals cross the natural numbers. That's the domain of the function. And that allows a signal to be zero at a Newtonian time t, then non-zero, then zero again without any evolution of Newtonian time. So we can now unambiguously have a discrete representation of this signal that unambiguously integrates to zero, okay? So a graphical rendition of this is that instead of a signal just being a function of a one-dimensional Newtonian timeline, it can progress through a sequence of values at each instant in Newtonian time. Now, it turns out the model of time is even richer than that in Ptolemy because we also recognize that in distributed systems and in any practical engineered realization of a system, all measurements of time are imperfect, and therefore we wanted to be able to model having a system with various imperfect measurements of time. And consequently, in a Ptolemy model, you can have a multiplicity of timelines coexisting in the same model. But I'll refer you to the Ptolemy book. Chapter 10 has a very nice exposition of that. And instead, I'd like to just conclude with a list of the people that I think are the primary contributors of the 208 that have checked in code into the Ptolemy base. And I apologize profusely to anyone who feels like they should be on this list, but aren't on the list because I overlooked them for some reason. And I also love this picture of my research group at one point taken by one of my former students, Chamberlain Fong. Thanks very much. And I'll take any questions that might. I'm not very familiar with Nango. I know what it is, but I'm very familiar with Simulink. And in fact, I've spent a lot of time with Simulink. And certain problems that arose with Simulink models are part of what motivated the work that we did with hybrid systems and this model of superdense time. And I think I'm fairly proud to say that our project has had some influence at the MathWorks, and subsequent versions of Simulink have actually bought into this concept of superdense time, and they're doing a much better job now than they were at the time that we identified these problems of doing hybrid system modeling and leveraging this principle of superdense time. So to some degree, we've had an influence on them. Simulink is really semantically very, very similar to our continuous director. It is now that it has more recently implemented some of this superdense time capability. I think the MathWorks people have been somewhat less successful at integrating Simulink with discrete event models. And in fact, they spun off a separate simulator that they call Sim Events for doing discrete event simulation. And to my knowledge, I don't think you can integrate Sim Event models with Simulink. I could be wrong. I haven't actually followed recent progress in that area. Since we've done it in Ptolemy, it's obviously possible to do it. But at the time that I looked at it, which was probably a couple of years ago, they were completely separate models and there wasn't a clean way to integrate them. And of course, in Simulink, you don't have any of the other models of computation like the asynchronous process networks or rendezvous models or synchronous reactive models or things like that.
Is your goal that everybody can do, I mean, most people can do all the modeling work in the GUI, or do most people end up having to do some Java too?
I think that initially the goal was that the library would be rich enough that you could do everything in the GUI. I personally have moved away from that rather dramatically. Almost every time I use Ptolemy, I write custom actors, and I often write them in Java, but even more often recently, particularly if they're just quick things where I need a sort of slightly complicated piece of functionality, but a little too complicated to want to build a graphical thing for, but where I have a clear idea of what how an imperative program would accomplish it. Then I just write it in JavaScript. And it's extremely easy to do that in Ptolemy. You just build it, pull in a naked JavaScript actor, and then you start writing JavaScript and ports appear and you can operate on inputs and produce outputs and write a script that translates the inputs to outputs.
But you're hardly the typical Ptolemy user. I mean, what do you expect other people to do? And do you most people doing it all graphically, or what's your user community look like?
So in my experience, most Ptolemy users zero in on a small subset of the system because it's a fairly dauntingly heterogeneous system. In part, that reflects the fact that it was essentially a laboratory for PhD level research for 26 years. And a lot of experiments are represented in there. And some of them, I would say, some of the directors you can find in Ptolemy have no users at all. Okay, they just have never been picked up by anybody. They're still in our regression tests. We keep them because, in part, we view software as a publication mechanism, and we have nightly regression tests that ensure that they continue to work. So if anyone, makes a modification to the Ptolemy core that breaks any of these more experimental pieces of work, we will get email within 24 hours from the nightly build that tells us that one of the regression tests has gotten broken, and we go in and figure out how to fix it. So, most people use a small subset. So for example, the Kepler project, when they started, they focused exclusively on the process networks domain. And everything they built was using the process networks director. And it was only as they got more familiar with the system that they started to branch out and use some of the other directors more richly. I would say the same is true of some of the actor libraries. So people who are, quite familiar with the machine learning toolkit will use it, but people who are not familiar with it, it's a little hard to just, drop in and start using it. It's easy to run the demos, and you can kind of figure out how the demos work. But it's a sophisticated enough library that you don't start using it within minutes. It takes a little bit more of an investment to learn how to use it. Yeah, I am very proud of the group that has done it. I think that one thing that really paid off was me being very hard-nosed about things like documentation and coding style. And, we've done very extensive design and code reviews of all of the core parts. A few of the experimental pieces of software have not been so thoroughly reviewed. And so the quality might be a little bit more sketchy, but the kernel of the system and the core packages have been gone over with a fine-tooth comb and are thoroughly tested with 100% code coverage in a nightly regression test infrastructure. And I think that's pretty unusual for software coming from academia, but it's also part of what enabled our use of this software as a laboratory, because when a new PhD student comes and has a bright idea about some way that they'd like to do discrete event modeling, they don't have to build the whole framework, right? They can just build the parts that they're focused on, and they can rely on the parts that are the things that they're particularly interested in.
Mm-hmm. Well, congratulations! I think you've done a great job.
Well, thanks. My hope is that there's a lot of durable stuff there. You never know. Software every piece of software has a lifetime, but it's designed to be durable. And but obviously, my hope is it will outlast me. We'll see.
Very good. Thank you.
All right. Thank you.
Thank you. Have a good day.
Yep. Bye.
Bye.